Hello. So, for today, I have to sort of apologize. It's only half prepared. I was traveling over the long weekend and somehow had two things half finished before, and now I have one thing still half finished, the other 3/4 finished. So let's see what we do. Originally, I wanted to show you about how UMAP actually works. I didn't get this properly finished because there's a couple of strange stuff inside that I wanted to have a proper look before I explain it wrongly. So I now take the other thing ahead and talk about diffusions and diffusion distances and connect it with that, the graph Laplacian and what to do with that. And in the end, we will get out of a whole thing in the middle of our path, we will get a few very nice pictures with nice patterns. And in the end, we will get an alternative way to define pseudotime and to make this trajectory through through the path, and to already show you, sort of tell you ahead what we are heading at the end. Imagine, you remember we have this adjacency graph where each cell is a vertex in the graph and each cell is connected with its 20 nearest neighbors, or possibly more in case the neighbors are not mutual. And then you can imagine a walker who just sits on a vertex in the graph and randomly goes to a neighbor. This is often called the drunkard's walk, because you imagine that the walker is drunk and just walks in a random direction because he doesn't know where it's going, or more commonly the random walk, because it's a completely random decision. It's a Markov process in the sense that the walker doesn't remember where he was a step before, and each step is again. And we can use this Markov process to define a distance by just defining the distance between two cells as how long it will take till two walkers starting at these 2 points until they meet. And that will turn out to be a very useful way of doing distances. And this is because the whole thing is connected to a diffusion process. So you all know diffusion. If you just put a blot of ink on some blotting paper, then it will sort of spread out slowly, and you can see by how it spreads out over time the amount of distance. And in order to remind us all about how this whole thing started, let's just quickly ask who remembers this thing. Who's a physicist here? It's the heat equation. It's the whole starting point of Fourier analysis. That was the equation that Joseph Fourier tried to solve when he invented Fourier analysis and harmonic basis function and all this. So how do we get to that? Now that I called it the heat equation, who has ever learned the whole theory behind this equation? Nobody? Okay. It's a good old, it's a beautiful piece of physics and of mathematics, even though the mathematics is rather simple because it's 200 years old, and it will turn out to be useful. But before we talk about cells and so on, let's talk about heat. So the question that Fourier had, imagine you have a long metal rod, which we heat up at some part. And we want to know how does the heat change? If I heat up this rod on that end, how long does it take till the other end becomes warm? And what I can, of course, now say is that I take the length of this rod here, x, and define a function u of x and t, which tells me the heat, how the temperature at the place here at a position x at time t. And you want to know how this changes. And because we are eventually will come back to single cells, and single cells are discrete entities, and we have only a discrete number of cells. We will do the thing that we will skip over the usual nice part, namely the limit to infinitely small parts, and to proper differential calculus, and we'll just split our rod into individual cells, which we number, and then we ask for each cell whether in a given time stop, this cell here will get warmer or colder. So let's say this is UK, and whether this cell gets warmer or colder in the next time step depends, of course, whether its neighbors are warmer or not. When the neighbors, if these two neighbors are warmer than the one in the middle, then the one in the middle will heat up because heat from the neighboring sides will flow in, and the other way, if these two are colder, heat will flow out. On the other hand, if this thing is, say, 3 degrees colder and this thing is 3 degrees warmer, let's say this is 20 degrees, 25 degrees, 30 degrees, then the amount of heat which will flow from the right to the middle will be the same as the amount of heat that flows from the middle to the left. So overall, we will get the same amount of energy coming in, it goes out, and the temperature doesn't change. So you already see the change in temperature should be proportional to the difference between the difference to the left and the difference to the right. So the change of UK at T plus 1 minus UK of T, so the temperature change of this thing should be proportional to some heat transport constant C times, and now I look at the difference to the right, UK plus 1 minus UK. This is the heat which flows from here to here, and UK minus 1, this is the heat which flows from the middle to the left one. And of course, what you see here is just the discrete form of a second derivative. So if we now make the limit to infinitely small time steps and infinitely small cell sizes, when this thing becomes du by dt is c times d2u by dx squared. So that was the heat equation. And if you want to, and we will see in a moment how to solve it. You will probably remember that you've learned this already several times, maybe under different, in different contexts. But for now, I look at this. The first thing we can notice, what would we do if we had not a rod, but a plate? And so I have here a whole grid of stuff. And so I don't have neighbors on top and the bottom, but also neighbors here and here and here. Then, of course, I have to add here to this the difference from the top one minus the middle one, from the bottom one minus the middle one, from the left, from the right one. So I take the difference from all different things, and in the end, then I have one pair of differences, which is one to the right and to the left, and one pair of difference to the top and to the bottom. And then, of course, I can here add d2u by dy squared, plus, if it's three-dimensional, by dz squared, or c is nabla squared u. So this is how we do heat equation. And instead of solving now the continuous case, and you can do as homework, or you can just remember how it works, we look at the discrete case. And in the discrete case, you've already seen here for each cell, we have to ask what are the cell's neighbors. What's to the left of the cell, to the right, to the top, and to the bottom. And as we are doing graph theory at the moment, because the adjacency graph was the thing we've always worked at, we might next ask, what is the, we might ask, how do we best derive this here? So, let's go from the grid. From a grid to a graph. And what we do here is we have a graph like this, our usual graph with vertices that we number and edges, etc. And we imagine each vertex has a temperature, and these are sort of heat bridges which allow heat to travel from here to here. we want to calculate how heat evolves on this graph. And what I do for this part is I again ask, what is the, so this is U1, U2, U3, so this is the temperature or the energy content at these different vertices. And for any vertex, I want to know how does the temperature at this vertex change. And I do this change at vertex I. I ask, how does dui change with the time t? And to do this, I have to go over all the neighbors j. So this here is the neighbors of I. So all the vertices j that are connected with I. And for each one, I can look at the difference, uj minus ui. This is the difference in temperature, and if the neighboring vertex j is warmer than our vertex I that we are looking at, then of course heat will flow to our vertex and the temperature of ui will go up. And if uj is cooler and this thing is negative, then the temperature will go down. And we have to sum over this whole thing in order to get to find out how much the whole vertex, how much the overall temperature of this vertex changes. And of course, we have some proportionality constant C, which essentially quantifies how quickly this heat can move through the edges. And in order to solve this for a complicated graph, what we do is we introduce a vector u, which is u1, u2, un. This is the state of the heat of a whole graph. It's a vector which is made up out of the temperatures of the different vertices, so it tells us the distribution of heat over the whole graph. And we want to write this now as a vector equation. To do this, what I first notice is that I can rewrite this thing by saying this goes here is the sum over the neighbors of I, uj, minus the size of the neighborhood times ui, because of course this part is always the same ui, so I can pull it out. I have here the sum over the heat of all the neighbors minus the heat on my vertex of interest multiplied by how many edges come in here, with how many it is connected. And now that I've written it this way, I can notice that I can write this thing here now as a vector equation, because for each component I have this thing here, which sums over all the adjacency matrix. A is the adjacency graph, H is the adjacency matrix. And you remember how we defined an adjacency matrix. Aij is 1 if I and j connected, and 0 otherwise. So this thing here, if I go in with a vector, with a unit vector u, which has only a single one at this position ui, it will put a 1 on each of the column vectors j. And this thing here can be written as du, where d is a diagonal of the degrees of the matrix I. So we take, for each vector, we take the degree and we write these degrees in the diagonal of a matrix. So in the first diagonal element, it has the number of neighbors of the first vertex, then of the second vertex, and so on. And now we have this thing here, which of course we can write together as A minus D U dagger. And that thing here we call the graph Laplacian L. So our matrix is now du over dt is Lu. Has everybody followed how we get this? The A is here that part where we go over neighbors, the D is the degree. With that we have defined this thing, which takes now here the same element, the same position as here we had du by dt is nabla. I keep forgetting my C here. Before I have said the time derivative of u is nabla squared u. You remember nabla squared is also called the Laplace operator or the Laplacian. And this thing here now takes the place of what was the Laplacian operator in the continuous case. This is why we call this thing the graph Laplacian, because it's the same thing and it basically mediates these kinds of stuff. And what we now want to do is, of course, solve this vector differential equation. Du by dt is Clu. Whoop. So du by dt is Clu. And to do that, we take the eigenvalues, the eigenspectrum of L. So we introduce the spectrum of L. So we say there is a group of eigenvectors LVI, like this. Right. We say we take the eigenvalues and eigenvectors of this Laplacian of this A minus D, and then we get this LVI minus lambda VI, and if we put this together, what then happens is we now find a solution. So we write u of t, expand u of t in eigenbasis or in basis formed by eigenvectors of L. So u of t is a sum of linear coefficients ai times vi, and these ai, of course, I have to make them time derivative. And that's what's happening now. I say that my state vector, which tells me how much heat is on each vertex of the vector, is made up as a linear combination of vi, because let's remember, the VI form a basis. Why do we form a basis? Because they are the eigenvectors of L, and L is a symmetric matrix. And symmetric matrices always have a complete eigenbasis, unless they are rank deficient. You see, A is the adjacency matrix, because we have an undirected graph. If we have an entry in ij, we also have one in ji, and this is a diagonal graph, so L is symmetric. Hence, we have a proper eigenspectrum. And I can now put this into my Laplace, into my differential equation. So I say du by dt should now be sum over all I. And let's put it like this. They say zero vector equals du by dt minus Clu. So this is just this equation written as sum over all I d ai of t dt. I just suppress this of t and just write dai of dt minus times vi minus C L A I V I. And because, and this is of course now, let's see if I do it correctly, dAI over dt Vi vi minus c ai, and now LVI is lambda VI, and I pull the VI outside of this thing, and then I'm stuck with this thing. AI by dt is C AI lambda I, and that, of course, is now a very simple equation. The change in this coefficient AI is proportional to itself, so AI of t is some AI of t naught times e to the minus lambda I CIT. Lambda I CT. The C is just a knowing constant that just allows us to convert between these T's and these lambdas. If we are physicists, we would simply absorb the C into the lambdas. And in the end, what you can now see is that the AIs fall off. So when we have any kind of solution, it falls off like this. And now this way, it still looks all a bit abstract, and the whole thing becomes beautifully more obvious if you actually try this out with an actual graph. And that's what I want to show you now. I get it to work. So let's see if that thing now switches on. Graph spectrum, here we go. First thing, in case you haven't completely followed the first thing I can show you, I wanted to quickly show you in case I want to, you want to look at it again. Here I found this beautiful, you don't have just these beautiful slides, which is essentially everything that I've written here in a rather unreadable handwriting in nice proper LaTeX. So here it's a little bit more of that. And there's also a bit more that we'll need in a moment. But now let's first try this thing out. I use the iGraph library, which is always our useful graph thing. And here I make this graph here from an edge list. So it means I have an edge from vertex 1 to 2, from 2 to 3, from 3 to 4, and so on. And with this iGraph package, you can say, plot the graph, and now you see here how the graph looks like. And what I now do is I can ask this graph package, give me the Laplacian. And as you can see, it does exactly what I tell you. Here you see the adjacency matrix, which has a 1 wherever I've put an edge. For example, from vertex 1 to 2, you have a 1. From vertex 1 to 3, from 2 to 3. So for all these edges, I have a 1. And in the diagonal, I have the degrees. Vertex 1 has 2 neighbors, so it has a -3. Vertex 2 has 3 neighbors, so it has a -3. Obvious corollary, the row sums and the column sums of this matrix are 0, because the diagonal element is always exactly minus the sum of the remaining elements. And now I do what I've just said. We have to calculate the spectrum of this matrix. And actually, you see, I've put a little minus here. Sometimes in some sources you find this as A minus D, in other sources you find it as D minus A, and either way around works, but depending on it, the eigenvalues will either have a plus or a minus, and you have to put a minus here or not. So I calculate the eigenspectrum. Now I have this here, and I say eigenspectrum $values, and here you see are the eigenvalues, and as you can see, the eigenvalues go down from the rather large all the way down to 0. Will they actually be the largest eigenvalue be 1? work now. So one thing which will turn out to be useful here later is, here are the vertices, and now let's first look at the eigenvectors. And the last eigenvalue here is 0. You see, this is essentially 0, and the corresponding eigenvector for that one is, which one is, how many have I put here? 1, 8, 9, 10. We have 10 vertices. The corresponding eigenvector is constant. It has the same thing on all of them. And that's pretty obvious, because if you take a state vector where you put the same temperature on all vertices, then this condition will be stable, because each thing will just give to each neighbor as much as they get from the neighbor, and everything is the same. Also, the eigenvalue for this constant distribution has to be 0, such that this exponential here becomes constant if we put a 0 here, because that is the stationary state to which everything converges in the end. We start with something, and after a while we get this. The heat diffusion, Wikipedia had this beautiful animation here, where you can imagine you start with a 2D grid, and on this 2D grid we initialize this with something, and then you can really see how it melts and melts out, but it doesn't stop, and you can imagine in the end the heat will be the same everywhere. And what we have to do is to construct this initial condition that you see here, this horseshoe-shaped or crescent-shaped area, as a linear combination of our eigenvectors, and then we can, and if we then evolve this function here, we will get the corresponding eigenstate. So, let's look a bit at how these eigenvectors look like. So here is for example, this is the last eigenvector. Everything has the same constant heat. This is the second to last, 9. It has here blue and here red. And this, you can imagine, sort of makes sense that this is a kind of a typical eigenstate. Being an eigenstate means if you evolve this state, the shape of a state won't change, only the amplitude. The difference between red and blue will become weaker and weaker until it's all equal. Why is this? The 6 is sort of in the middle. It gets as much heat from the right as it loses to the left, and that's why it overall hardly changes, in this hence white. So I use the color scale which has white in the middle. It gets a little bit more heat from the right, it seems. Also, you can see here edges like these. You can imagine how these here on the outer side, they always have to push heat to the left, and the heat is pushed from the right to the left and ends up here, and overall the distances stay a bit the same. Overall the shape stays the same. We will see a bit clearer in the next graph that I show you, but for now this is an obvious way where you start putting all the heat on the right and it moves to the left. If you use the second eigenvector, here all the heat is put in the middle and it moves outwards. Here it's a bit more complicated. Heat is put here, and it sort of diffuses in the left half. In the left half of the graph, heat diffuses from the top down, and in the right half it diffuses here from the right inwards, and overall the two wings of the graph diffuse it inwards. But overall, this graph, I plotted it and looked at them a while and found it not too clear what's happening there. Then I went back to the same thing that also Fourier thought, and thought, let's make a big grid. So I make here this grid matrix of 30 by 30 vertices, so 900 vertices. And they are arranged as a 30 by 30 grid. And I connect each vertex, I connect with its neighbors to the top, bottom, left, and right. And as you can see, the vertices are numbered in columns from 1 in the top left till 900 in the bottom right. And I made this matrix R here, which just contains all these numbers from 1 to 900 in order to give each one a number. And if I now ask, in my grid on grid position 10,7, what vertex is there? It tells me it's vertex 190. And if I go 1 to the down, it gets vertex 220. And if I go 1 to the right, it's vertex 191. So this is how this works. And now I want to make a graph. So I tell it, make me an empty graph with 900 edges, so L squared. And then go from 1 to 29, so through all the columns except for the last one, and always connect the column always connect each vertex with its right neighbor. So you see this is the ith column, and this is the I plus 1th column. Here I say connect each one with its neighbor to the right. If I want periodic boundary condition, I could also add a last line which then connects the last column with the very first column. I leave this uncommented, and we can put it in a moment to see what changes. And now I do the same for the rows and connect each vertex with the vertex right below. And now I have this graph. Let's see if I say plot G, how it looks like. Yes, you see the vertex, the algorithm hasn't quite managed to realize that this is just a square grid, but it is. So if I've double checked it, I do this. Now I can ask for the Laplacian matrix, and this time I plot you the Laplacian matrix as an image, and it's maybe a bit hard to see here, but you can imagine how the Laplacian matrix should look like. Let's first see how the adjacency matrix should look like. If this is the matrix, and here's the diagonal, each vertex is connected with its neighbor to the right. So this thing is connected, so we should see these here, sort of these lines. And there's always gaps because I haven't made periodic boundary condition. And of course, I also have everything connected to a vertex 1 down, which is 30 to the right, so I get this here. And this on both sides. And you can sort of see this a bit if you squint here, that it looks like this. In the middle, of course, you have the negatives. Now I get the I ask for the eigenspectrum of this thing and calculate all the eigenvalues. And what I will now do is I ask to calculate, stop before I do this. You should have first looked at the eigenvalues before showing you the eigenvectors. So here are the eigenvalues. And let me plot them quickly. So these are the 20 smallest eigenvalues. And you'll see in a moment why I've plotted the smallest ones. As you can see, the last ones were at 0, and then they sort of go up. If I plot them on a log scale, you can see that the very last eigenvalue is more or less 0, while all the others have more or less reasonable values. We've already argued that there should be one eigenvalue which is exactly 0 and which is connected with the eigenvector of all elements having the same heat, and that's this here. The last eigenvalue number 900, with the value 0, and this vector where everything is the same. This here is now the vector 899. And as you can see, it sort of makes sense that this kind of vector would be stationary, where all the heat is here and all the coldness is here, and heat flows over there. After a time step, everything will stay the same because the overall pattern will sort of be the same. It will just, the slant be slower. The equivalent here for our rod would be just an eigenthing which just looks like this, where it's hot here and cold here, and after a while, because everything moves a little bit to the right, and the amount of heat that moves in every moment is always the same, because the slope is constant here. after one time step, it looks like this, and like this, and like this, and you see it's all proportional to what you had before, if you put the 0 here. And that's also what's happening here. If you go back to 898, we see exactly the same pattern the other corner. And you see this is a degenerate eigenvalue. Both of the eigenvectors have exactly the same eigenvalue. So we have a whole eigenspace in a way. Any linear combination of these two initial positions will keep its shape and will not change its shape and only its amplitude. If I now go back to the next higher eigenvalues, I get here this nice pattern, this here, and as here you see we heat the corners and have the heat sink in the middle. We heat here and we have sort of a mixture of going up and down. And once I get to higher and higher eigenvalues, the whole thing will get more and more, will look more and more periodic. Let's look, for example, at this one, where you can already sort of see this is like if you take the cross section along a line, this is a sine wave. Why would a sine wave be an eigenvector here? Imagine our rod is very long, and I have a sine wave, which keeps periodically repeating and repeating and repeating. The change at any point is proportional to the second derivative. And the second derivative of the sine is minus the sine. So the second derivative is proportional to a value here. So of course the sine does change its shape. Here this maximum just pushes heat to both sides and stays the maximum. This part here with curvature 0, the second derivative 0, will stay at its heat because it always just moves the heat move. This will move up, and after one time step it will look like this. So if you have periodic boundary condition, or if I make my grid infinitely large, all the eigenvalues should look like this, should look like sines and cosines. And that was the point where Fourier realized that that in order to write down his universal solution to his heat equation, he needs to use sine and cosine functions. That for this plate that we had here on Wikipedia, in order to write this, we have to come up with an eigenbasis made of sine and cosine functions exactly of this shape. And we have to set up our initial condition as a suitable combination of these things. Quite obviously, if this here weren't the first derivative, but the second derivative, what we have is instead of a heat equation, the harmonic equation. And what we see here is sort of a plate which bends and moves up and down. And well, this would be a string of a violin. The force moving this down is proportional to it, and hence the whole thing swings in that case instead of relaxing to constant things. But the eigenfunctions are exactly the same. This is why these pictures that I show you here on my graph, all these here, you might have seen them before under a completely different name, namely Chladnische, why is it German suddenly? Let's switch to English. Chladni sound patterns. What he did is he used shapes of sheet metal, like here this sheet metal square, which is very much exactly like this one here, and put sand onto it, and then he used his violin bow to make this thing vibrate, and everywhere where it vibrates strongly, it throws away the fine sand, and only in the knots which don't vibrate and don't move, the knots stay put. And when you see this pattern of sand which stay where the nose stays put, and if you compare this old picture of some 150-year-old physics textbook with my plot here, if I switch a bit, I should be able to find, here it is, exactly the same picture. A cross in the middle, both here and here. I found this very satisfying to see my old physics textbook by doing this little thing. Funny enough, also, I didn't put any sign into it, they came out. Obviously, I don't have exact signs because I have here this fixed boundary. If I switch over to periodic boundary condition by just adding these extra edges between the right-hand border and the left-hand border and recalculated my eigenvalues and all of them, then let's give it a moment. I get really here sort of proper sine waves. Here's one sine wave. Now, of course, because the boundary conditions are periodic, the phase is no longer aligned with my graph. It's just a numerical coincidence about where this moves up and down and whether it's vertical or horizontal. But here you see this typically exactly square sine wave eigenbasis that is typical for the heat equation where this goes down and this goes up, and which is also the starting point of all continuum mechanics, where you also always put things in sine waves. So, what do we do with this now? The next thing I want to do is to tear this grid. I go back here to my thing, maybe let's put the periodic boundary conditions out again. Make the empty graph a matrix. And now I make a second graph in which I put the edges I want to remove because iGraph is this graph difference function. So I remove all the edges between the 10th and the 11th row, and I remove the edges in the 10th row between 4 and 5. So I tear my grid now like this into 4 pieces by removing all the connections here, all these connections, and I remove all these connections by taking this set difference. And I recalculate my eigenvalues. And what now happens is, if I look at the eigenvalues, you will notice I have 3 zero eigenvalues instead only 1, because I have 3 connected components which are disconnected to each other. And hence, obviously, if I put a lot of heat onto one of them and not onto the other components, the heat cannot flow in the other parts of the components of the graph. So I have not only one stationary condition, but I have a whole space of stationary condition, namely any superposition, any condition where all these things have the same, where all these vertices have the same temperature, all these vertices has another but constant constant, and this has a third but constant constant. All this is a stationary thing which cannot relax any further. So this is why I now have a degenerate eigenspace of three dimensions, which are spanned by having one value here, one value here, and one value here. And of course, the next eigenbases were all always only affecting one of these parts or strange combinations of them. So in a way, what we now have is actually the eigenspectrum of 3 different of these rectangles just smashed into one matrix. And while I click here, I always see a pattern of one, of the other, or whatsoever. Sometimes 2 of them fall on the top of each other, but here you see how this now looks. Each value is typically only associated with one of them, sometimes with 2. Why is this of interest? Because let's now see what happens if I reconnect the 3 components by putting in one little edge here and one little edge here. Actually, so I put in a single edge between 10 and 11, somewhere here, and I put in one somewhere here. Actually, if I now change, this is what I tried before. So I add 2 edges so that the 3 parts of my graph are no longer completely disconnected, but only nearly disconnected. And the reason I do this is because this is the thing that we had quite often in our adjacency graph of the that we had in our initial in our single cell data, but we had a whole blob of cells which are similar, cells which are very different, and between them a narrow connection with maybe only 2 or 3 cells which form the connection between them. So I want to see what happens in that case. And if I now look at that, because that it's now only because the graph is now completely connected, my eigenvalues have now changed a bit. I again have only 1 zero eigenvalues, but I still have 2 eigenvalues which are much smaller than the others. And these 2 eigenvalues are associated, still seem to span the eigenspace that we just were looking before, where we have always only weight in one of the components. The vectors now mix a bit, but it's still sort of similar. And then you can see here you see the edge that I added, and here's the other edge that I added. And now you see things sort of stay connected, or maybe not quite. And if I go to higher stuff, then they connect a bit more. But the lowest eigenvectors, even though the eigenvalue is, in the case of fully disconnected graph components, I could immediately notice the number of connection components by looking at how many zero eigenvalues I have, and by looking at the eigenbases associated with the zero eigenvalue space, I could see what the components are. And now, with them being nearly connected, but only slightly so, this degeneracy is lifted, but only slightly. And I still have my 3 very low eigenvalues, which are much lower than the others, and this still allows me to do this. So I get a continuous change from having a connected to a disconnected graph. I could add here more and more edges to slowly go back to our original case, and in this way, I can get this feeling of 2 parts of the graph being not properly connected, but also not being entirely disconnected. And that is useful when we analyze graphs. And this whole idea runs under the term spectral clustering. Whenever you have some big data cloud and do a neighborhood graph, you can use the spectral clustering to see which parts are densely connected and which parts are not so densely connected. And I thought, and that's now unfortunately only half finished because I quickly tried this before just half an hour before the lecture. I used our usual matrix that we always had. You remember here our typical standard data set where we have our stem cells here, and when they are doing their transition, and then they move here to the neural stem cells and switch to the neurons. You remember we noticed that there should be a connection between the neuroblast and the neurons that is easy in our interactive sleepwalk visualization, but here it's a bit hard to see because UMAP has torn it apart. But now let's see how the eigenspace of this graph looks like. So I do exactly the same that I just did with grid with this adjacency matrix. So what do I do? Here, you remember we had 18,000 cells. I use my nearest neighbor thing to get for each of these 18,000 cells, it's 15 nearest neighbors. And now I construct the adjacency matrix associated with this neighborhood graph. This time I thought I'd show you a new way how to do this very conveniently in R. I use R's sparse matrix functionality. So this is a sparse matrix. A sparse matrix in reality, in this case, it looks like this. It typically has 3, in the easiest case, it has 3 vectors, a vector I, J, and X, I, which lists all the non-zero elements of the matrix. X are the values, and I and J are the row and the column indices of that. Here I started by telling it I want a sparse matrix with no data at all. So it's a completely empty matrix with only zeros of this size. And now for any neighborhood, let's for example take the second nearest neighbor. Then I can look here in my $NN index. If you look at this is for each cell the second nearest neighbor. And if I now say I want in my matrix an entry for like this here, 1 and cells, comma, j equals, let's do it like this, data frame. I do this, when you see, comma k, when you see here, I now have table. Here I have always in row 3, color 9, 5, 12 of a matrix, I have an entry. And this entry should be just a 1, comma, x equals 1. So this here, if I now, instead of saying tibble, I say sparse matrix. And just to make sure that it understands that the dimensions are the same as before. I now get a sparse matrix which has a which has ones to connect each cell with its second nearest neighbor. And I do this for the first, second, third, fourth nearest neighbor, going through all the 15 nearest neighbors and always making a sparse matrix with ones at this thing. I add this to the sparse matrix I already have. And that way I build up my adjacency matrix. And now in this adjacency matrix, each column, each row contains a 1 for the nearest 15 nearest neighbors of this thing. An adjacency matrix should be symmetric. So I add the adjacency matrix to its own transpose. And now I have a symmetric matrix. But occasionally it might happen for half of the vertices, I probably got them twice because I got them in the list of neighbors of I to j and in the neighbor of j to I. And others might have appeared only once. So if I now look at this matrix, and at the end of this matrix, I see the following. That here I see again it's now with i's and p's. Never mind, here you see the values, the non-zero values, and they are always either 1 or 2. If I got it twice, then there's a 2. Luckily, this is easy to rectify. I just tell them to replace all of these values by 1s, no matter what it was before. Like this, I say all the non-zero values should be 1, even if they had been a 2. And now I have a proper adjacency matrix. Now, the next thing is I need for my graph Laplacian, I need to subtract from the adjacency matrix this diagonal matrix which contains the degrees. So what do? I again say I want I want all the numbers from 1 to 18,000, in J2 from 1 to 18,000, so it's just the diagonal, and the values in the diagonal should be the row sums of the adjacency matrix, because these are the columns. And I call this the degree diagonal matrix, DEC-DIAC, and I take the difference between the DEC-DIAC and the adjacency matrix, and so I get my Laplacian matrix, LAPLM. And I calculate the eigenvalues of LAPLM. This time, instead of the Erlbar package, I used the RSpectra package. I discovered this only recently that this works better, because this RSpectra package has this function where you can tell the Landkos algorithm whether you want the 20 largest or the 20 smallest eigenvalues. And we've just seen that for this graph spectra, the interesting thing are the smallest eigenvalues, because the eigenvectors associated with the smallest eigenvalues are associated with a large-scale structure, with a big blocks of disconnected or nearly disconnected parts of the graph. Let's look at the eigenvectors, and as we can see, two of these eigenvectors are practically zero, so we have two completely disconnected components. And then we seem to have another component which is also quite badly connected to the others, because there's a factor of 10 here in between. Let's look at them. What I now do is, needs a moment. I plot these eigenvalues. So this was the smallest eigenvalue, the one with 0. And as you can see, it has one color on all these and another color on that one. And if I look at the other one, it's the same picture. So this is this degenerate eigenspace to eigenvalue 0, where we essentially have one basis vector which puts all the weight here and another basis vector which puts all the weight on the rest of them. doesn't quite look like that because the two eigenvectors that we've gotten are not these pure eigenvectors, but some mixture of the two. So we are somehow rotated in this zero eigenspace, but we can still clearly see this is one component of the graph which is completely disconnected with the other component. Now I can look at this other one, 18, which is this one. So this thing here is also more or less disconnected, but the eigenvalue for the 18th eigenvalue wasn't zero, the third smallest. It was only nearly zero, so there must be one small connection here, which still isn't in. So, and this is the beauty of spectral clustering, we got this out for free out of a thing. Now we can go back to the next one, and now things become a bit clearer. Now we have this big blob is the next one, which seems to be disconnected from the rest. While that part here, because it's not that disconnected, we still only get sort of a spread. So we see that this red one, because it's not completely disconnected, seems to push a bit of its heat to here, where it needs to then slowly equal out over that. And we need to have this, and within this big component, our lineage, as we used to call them, we now see that we put the heat here at the stem cells and the coolness here at the neurons, and they, of course, have to meet in the middle to equilibrate out. And this is more or less the same concept, now looked at it from the other way around. And here we see another one, which suddenly turns up, a completely disconnected, very small one. Now these things, and now we start to look more into the connected ones. Even for occasionally, we still see disconnected individual parts looking up, which are now not properly sorted as the lowest eigenvalues, probably because they are so small that they look a bit strange this way. What I found in experience, what makes sense is to find all these disconnected parts, or hardly at all connected, remove them, and then recalculate the vector. And then in the remaining stuff, if you recalculate it for only those vertices which are now all more or less reasonably connected, then you start to see the sine waves which sort of go along the whole length. And this is now useful because I told you in the beginning we want to make it pseudotime. And as you can see here, sort of our sine waves, they seem to sort of already match out with pseudotime. We had this quite nicely, if I now find it again, in that one, where we see here going from red over white to blue. It's quite clear that the argument of this half sine wave, or whatever it may be, is the pseudotime, which we also calculated last time with our principal curve, only doing now in a different way. And we can discuss next time about why exactly these things are not really the same and where the difference are. The crucial part is we have now ignored completely the distance. We have completely binarized our data and only look at and only say either it is a neighbor or it isn't. And surprisingly, we have lost very little information due to this binarization. And that's something we will come back to when we talk about how UMAP work next time, where the inventors of UMAP didn't appreciate it, but others noticed it later. If you completely binarize the stuff, kick out all the distance information and only keep the adjacency matrix, UMAP still works as well as it did before. Which was a bit of a pity for the actual authors of the UMAP paper, because they wrote about 15 pages about how important it is to calculate these continuous distances correctly and how to normalize them. And then somebody comes, you just kick out all this math and replace it by zeros and ones, nothing changes. Which is a story we will look more into next time. And because this is sort of still something in open debate, we can also discuss about who we believe in this field. But now I first want to show you how do we make something out of this. And here, this way of putting reading off the trajectory is a little bit unappealing because it's not really continuous. We have to invert this sign here. And we've already seen these are not really sine waves because of the boundary conditions. So that doesn't work that well. So we have to, and we can find something that works slightly better, or that works much better. And we get there by remembering that there's an alternative way to understand heat. Typically, when we talk about this heat, we call it diffusion. And diffusion is a stochastic process. And there is two ways how we can understand diffusion here. Why? In my first derivation of the heat equation, I said we look at the difference between the temperature here and here and say the amount of heat that moves from here to here is proportional to the difference between it. That's how Fourier started, because that was sort of the empirical observation that people did, that we noticed the speed with which heat moves seems to be proportional by the temperature difference. But there's another way how you can look at it. You can imagine that heat is made up out of individual parcels of energy. In physics, we would say phonons. And we can assume that these things, that these parcels of energy, they move randomly. Let's say we have 1,000 energy parcels here and 2,000 energy parcels here. At any given moment, a certain percentage of these energy parcels decide to move to one of its neighbors. So at any given moment, an energy parcel decides with a given probability P to leave its cell and move to one of the neighboring cells. And it does this randomly. And then you can imagine that this moving to a neighboring cell has exactly the same effect, because if there is twice as many if there is more heat particles, if we have two cells in contact and one is hotter, it contains more heat particles than the other, and each of these heat particles move randomly to the other cell, then of course it will equilibrate, because more will move from the one where we have more to the one where you have less. This is the same that you know in thermodynamics when you look at gases, where you also say an atom might move from an area with higher pressure to an area with lower pressure. In reality, the atoms don't get moved by pressure. They just completely move randomly and bounce into each other, and they bounce so often that their direction is essentially random. And the only reason why we get from the higher density a flow to the lower density, that in net effect, more of them randomly go to the left than go to the right, simply because at the beginning there have been more at the right who could start from the right and go to the left than the opposite direction. If we use this kind of thing, then we can decide to take a single heat particle and follow it. So we imagine everything is cold and only this thing is heat, and it contains one heat particle, and we want to follow it. And in each time step, this heat particle decides to leave its cell and goes to a neighboring cell. And that's what you call a random walk. And in our random walk on the graph, we start at one point and we go to a neighboring point. And now we have to think about how to calculate this random walk. And I quickly show you how this works. Let's see if I manage to write this properly on my board. And I do this now slightly different. And you'll see instead of a Laplacian, I now have something which I call the diffusion kernel, and it looks a bit different, but it will give us surprisingly the same effects. Again, we have our adjacency matrix A, and we have our Walker. So we start off with some U naught, which is this time I use discrete time. I don't go into a continuous time limit, I make steps, and in each step something happens. So at step 0, the Walker is with probability 100% on node K. And now I wonder what happens after the Walker has moved to a neighboring step. And to so if we have, this is the matrix K and these are its neighbors, then the Walker will move to one of these neighbors with to each of these neighbors with probability 1/3. What I can do for this, I can now take my adjacency matrix and multiply U0 from the right onto it. And then I get, of course, a new vector which has a 1 here, a 1 here, and a 1 here. This thing is 0, and all the other vertices are also 0. But I wanted probability, so that the probability of a walker being on any vertex adds up to 100%. So I want this to be a third, this to be a third, and this to be a third. So what I do is I take again this degree matrix, but 1 over the degree. So if I come in from the right with a matrix with a vector which has a 1 at position k, and the vertex k has degree 3, then this diagonal matrix has a 1/3 on k, so it changes this to 1/3. And then each of these 1/3 is pushed to one of the 3 neighbors, and so afterwards we have something which has a third here, a third here, a third here. If, however, the walker is not at one point, but the 50% probability it's here and the 50% probability it is here, then of course what I've just described will happen in parallel for both of these vertices. These 50% probability will be split, divided by 3, giving 1/6 each, which goes to each of these neighbors. And the other 50% of a walker, which was maybe here on another vertex, will also add something. So if I have this thing, and I call this the transition matrix T, I have this nice thing that this thing preserves the sum of all the matrix elements. So TU is the same as U. So I write here U1 because this is an L1 norm. It's not the usual Euclidean norm. It's the norm which I get by just adding up these elements. I call U here a stochastic vector. Stochastic vector is just a fancy way of saying it's a vector whose elements are between 0 and 1, and they add up to 100%, because that way they represent a probability distribution over the vertices. And if I give it to the T, then I get go here. And now I want to try that here, how this works. So what I've done, let's see, where have I put this? Okay, I've chosen a cell, and I've decided I want to use this cell here. You can't see that. I've chosen a cell here at position somewhere here in the middle of this area. I wanted to get it somewhere, so I decided I take the cell which is closest to the point -6,6. So I take the UMAP coordinates and calculate the distance to the point -6,6 and take the index of the smallest one, and now I see the cell number 14741 is a cell here. Now I make myself a vector which has a 1, which has 0 everywhere except for a 1 at this point here. So this vector has only a single 1 at this element. And if I now multiply it from the left with the adjacency matrix, then this 1 gets spread out. And if I now look at which greater 0, it tells me now all the neighbors. And of course, at all these places, it's 1. But I want it to be not 1, but I want these ones to be add up. So if I calculate the sum now of this here, the thing happens that I've just mentioned. Our 1 walker has spread into 24 walkers, but I want the probability, so I should divide this by 24, and I should do this beforehand. So I calculate this, I make this diagonal matrix, which has 1 over the degree in it. So I construct this here by taking the degree diagonal matrix we had before, but I replace each value by 1 over the value. And now by putting this D matrix in it, I now get something which is always 1. So I have here my transition matrix, which is this adjacency matrix multiplied by this inverted degree diagonal matrix, and that one has now the property that it's a stochastic matrix. That means it preserves the norm. And it preserves the norm because the call sum of each, the sum of each column is 1. Now I go again in with my sparse vector at 1. And here you see where this my probability distribution, here is my single 1. And everything else is 0. Now I multiply it with this sparse vector. I multiply it to the right with my transition matrix and make a new plot to see how it looks now. And as you can see, it has spread onto these 24 cells. Here I always calculate with my step variable how often I've done that, so you can see a bit how this now spreads. 3 steps, 4 steps, 5 steps, 6 steps, 7 steps. You can see here really the typical diffusion process where you put a piece of ink here onto this piece of blotting paper and it spreads out. And you can already see how this can be useful to help you get a feeling of, to get some kind of diffusion distance by seeing how far points are from each other and how difficult it is to reach another point from here. But as you can see, the spread is quite slow. We have to make, we shouldn't put too much, we have to make quite many steps. And obviously we don't want to calculate 1,000 steps. So we should calculate this here properly. What I want to do is, I want to do n steps in one go. How do I make n steps in one go? After n steps, I have, of course, t to the n times u naught, because I always multiply with t from the left, and I have this t to the n times u naught, and I don't want to carry out this multiplication n times. So you can probably already guess what we do in order to get this properly. We have to calculate our matrix exponential here with an eigendecomposition, which is not as easy because this is no longer a symmetric matrix. We have to multiply it from the right with this d, but not from the left, so we cannot properly symmetrize it. So, but there's a trick to get this fixed. And I do this as follows. I say Tn is a d to the minus 1 to the n. And now I write this out as a d to the minus 1/2, d to the minus 1/2. So I have here once, twice, 3, and I say this is n times. Now I read this slightly different and say this is once, twice, 3 times, also n times. And you can see here the first part of this, if I now have shifted this division, the first part is missing its left d to the minus 1/2. So I have to write this extra, d to, so what I now have here is d to the minus 1/2, a d to the minus 1/2 to the n. That's this middle part, but on the left this is wrong because there we don't have a full product, but the d to the minus 1/2 is missing. So to compensate, I have to put a d to the 1/2 on the left hand right. On the right hand, I have a d to the 1/2 left over, minus 1/2, so I have this thing here. Now this thing here is symmetric. And because it's symmetric, we can diagonalize it. And if we diagonalize it, we get a matrix lambda which has the eigenvalues of A in its diagonal. And we have matrices U and UT outside. So we say this is d to the 1/2 u lambda to the n ut d to the minus 1/2, where u and lambda are the eigenvectors and eigenvalues of u, lambda eigensystem of d to the minus 1/2 a d to the 1/2. Let's try this out. So to do this, I've prepared these two matrices. I make here the matrix d to the minus 1/2, square root inf dec dirk. I've called this is d to the minus 1/2, and square root dec dirk without the ins is d to the 1/2. Now, of course, you can't see that maybe. So we want to calculate this thing here, d to the 1/2 u lambda to the n ut d to the minus 1/2. So I do this by saying d to the minus 1/2 times a, the adjacency matrix, times d to the minus 1/2. I want to get the 100 largest eigenvalues of this thing. Call it Eitrim for the transition matrix. Here's the eigenvalues, and as you can see on the first hand, it doesn't look that great. The eigenvalues don't go down that quickly. Remember, this is an 18,000 by 18,000 matrix. We take the eigenvalues, and we hope that we can get away with only looking at the first 100 eigenvectors. It is really okay if the eigenvectors you see is going down like this, but imagine we want to make 100 steps. Then you can see that this eigenvector here is 1, and the 100th eigenvector is already 10 to the minus 8, because we took it to the 100th power. And this is really annoying. And obviously, this lambda to the n in the middle will suppress all the other eigenvectors, because it multiplies it with a really small value. So we shouldn't make too much mistake by keeping only the top 100 eigenvalues and correspondingly also only the top 100 eigenvectors here, and keeping the rest differently. And now, let's see if I manage to, my notes end. Now I will make the brave attempt to do this manually, what I have to do here now. So I take my initial matrix here, my sparse vector, which has a 1 only here. Now, in order to do this, I first have to calculate it with how did I call it? Square root inf dirk. And so I'm now writing from the right to the left. And then I have to make this U matrix, which is UT, which is Eig transition matrix dollar vectors transposed. Percent star percent. Now we get this here. This then times the eigenvalues. Eigterm dollar values to the 100th power, because I wanted the 100th one. What happened now? I have to make this a diagonal matrix. So, and then I have to go back with my eigenvectors. Now you see something annoying is happening. Now it takes long. Why that? Because up to here the whole thing it went down to a vector of only 100 elements, and now it blows up again. And that will be the trick that I'm not sure if I managed to do so, but I'll show you next time, is that we say we stop here and we omit going back to this U space because it's a rotation anyway, only. And by saying we stay in this space here, where we are not rotated back, so in the space in which we get projected by this, in which we get moved by this rotation, which is spanned only by the top eigenvectors, we move into something called the diffusion space. And in this diffusion space, we can compare two vectors. We can compare two vertices by just asking how far are they in this space. So what we will do is we will say diffusion distance between cells I and J. For this, we first take here this lambda to Vn ut d to the minus 1/2 ei. So this is the unit vector which has a 1 only at cell I and 0 everywhere. And we do the same with the other one, lambda n ut d to the minus 1/2 ej for n steps. And we call this the diffusion distance. So what's happened here is we take this EI, normalize it a bit with this distance matrix. When we move it conceptually through our transition matrix n times, but what we'll get in the end, so what we have here, this here, is the same as taking the transition matrix to the nth power, EI, with d1/2 u minus d1/2 u tn ej. And you can see if you ignore this, if we assumed that this d1/2 were, if we ignored that for a moment, if we assumed that all the cells have the same degree, then we could also omit the u, because the u is a rotation matrix which rotates in our eigenspace, which is made up by the eigenvector. So the Euclidean distance is invariant about it. So this is roughly the same as t to the n ei minus t to the n ej. And by roughly the same, I mean something strange has happened, because when I calculate this Euclidean distance, in order to get the same that I get here, I have to weigh the components slightly different. Typically, you would add up, you take the difference in each coordinate, square these differences, and add them all up. But here we make a weighted sum of the components. Each component gets weighted by this d1/2. So it's this thing with a Euclidean norm weighted by d1/2, where each component gets weighted by the thing. So a vertex with degree 20, a vertex with degree 20 will have twice as much weight in this Euclidean distance than a vertex of degree 10. Why do we do this? Not because it makes sense. It doesn't make sense, but it doesn't change much, because all these vertex degrees are more or less the same. They are somewhere between 10 and 20. But if we decide to take this hit and accept the fact that our different components are not all exactly the same weight in the Euclidean distance, we gain something useful, namely that we can calculate this Euclidean distance between the diffusion spaces after, in a very rapid way, even for a really large n. Specifically because we can do the whole thing in sparse space. As you can see with U here, if this is a matrix, now here I have to say, this UT here is a vector formed only by, that we can form just with the top 100 eigenvectors and ignore the rest because it will be suppressed by this lambda n anyway. So these vectors here, they live not in an 80,000 dimensional space, but they live in a 100-dimensional space or so, because we only take the top 100 eigenvectors, just enough eigenvectors that the following one gets suppressed. And this allows, and what this here is, it's sort of a, now unfortunately, start a new session. Now it has just had the plot up here. You still remember the plot in a moment. So what we had, if you remember, I had here my thing here, and I had one point and said, let's evolve 100 steps, and I got something like this here. And now I have another point, like here, and I evolve it 100 points, and I get something like this here. And what we essentially do here, by calculating this thing here, is we ask what is the overlap between the diffusion blob of this cell and the diffusion blob of that cell. And that tells us how far they are apart. And that's a useful aspect. And of course, the value that we get here depends on the n. And we have to talk next time a bit about how we choose this n well. And actually, the literature here is the way how it's usually done is, in my opinion, not quite optimal, but we can see this later. And the beautiful thing is now we have gained, so the point is we now have gained another dimensional representation. We went from our PCA space now to this diffusion space where we need only a couple of components. 100 was generous. We could probably go down to 10 or so to still get a good approximation here. But we will have to play with a couple of different n values. And because for the n value, the number of transitions that we make depends on how big these blobs are, it allows us to explore the structure, the topology of our point cloud on different scales. We can, for n equals 1,000, the distance from here to here will essentially be 0, and the distance from here to here will be something, and the distance from here to here will be infinite. While for t equals 10, it's different. So this whole thing gets a sort of non-linearity, a sigmoid shape, where you have some region where the diffusion blobs completely flow into each other and become undistinguishable, like these 2 points here, where the diffusion blobs don't meet at all. So this would be a distance 0. Here, these don't meet at all. This would be a distance infinite. And an area in between where we get something. So our real original Euclidean distance, our original PC distance, PCA distance versus this diffusion distance gets, yeah, some sigmoid shape. And by choosing our n, we can put this ramp of a sigmoid to different scales and can hence check how things change on a large scale or a small scale region. And that makes it a useful a tool to understand the topology or the scale-dependent shape of this data. And now it's 5:30. I've talked about 90 minutes and conveniently reached the place where I run out of my notes. I could switch over to the notes from last year's course, but where I made this whole thing started it from exactly the opposite end, so it doesn't fit together. So now I have a week to prepare the rest and do this. What should we do with? I might do this on Wednesday, and whoever wants to can help me prepare it, or help me explore these things by doing this now onto the real data and checking out and seeing how we get beyond this part where my computer just crashed. So that would be this week's Wednesday exercise in case somebody wants to try around a bit with this data. For the others, we see each other on next Monday. What we also maybe should start thinking about is who actually will need a grade. 1, 2, 3, 4, 5, 6. Okay, when we should talk about this later. One thing we could either make an oral exam, another thing we could make is to make a little programming project where we pick out something like this and say, okay, now make a nice demonstration of the math and how it works in practice or so. But we can talk about this next time. So overall, something like 6 people or so. Good. Then hope that was sort of an interesting walkthrough how we use graph theory to, I mean, you might have noticed this is now in a way, I call it single cell data, but this is applicable to any kind of big feature space data that you might find in any kind of machine learning. And so I hope it's also a bit more general than just biology. Okay, see you next week.